All right, so as I was saying, differential equations might be one lesson in our, course, in our curriculum, but it is a whole course of its own. It's a whole division of math on its own, differential equations. So you can do, oh yes, yes. So yeah, it's huge. Like differential equations, like they're a whole other world on their own.
I saw memes about it.
Yep. So a differential equation is an equation involving a derivative, and differential equations have orders. We talk about orders, and the order of a differential equation is the highest derivative in the equation. So for example, if it's dy dx, that's first derivative. We call it a first order differential equation. If it's d squared y dx squared, that's a second order differential equation, and so on. And and they're like they're their own entity. So those might be different chapters in that course, let's say, right? Like second order differential equations is a whole entity of its own, and so on. All right, so let's move on here. Okay, what we're going to do here, the question is asking to find all functions y that satisfy dy dx equals this. So basically, we want to find any function which, when you take a derivative, will get you secant squared plus 2x plus 5, right? So we need to find all functions. That's the important part. So now what we do is we start with what we're given. So it's dy dx equal to secant squared x plus 2x plus 5. Now, what I'm going to do is multiply both sides of this by dx. Okay. What I have now is dy equals secant squared x plus 2x plus 5 dx. And now I take an integral of both sides. Okay? All right. So now I'm going to integrate the left side separately and the right side separately. So do you see how this separated the equation so that all the y's are on one side and all the x's are on the other side? So in the first case, this is the integral of y. So what is the integral here? Technically, I have 1 dy, right? And if I take an antiderivative of that, it'll be y plus c. Okay. Equals to, now I'm going to take the antiderivative of the other side. So integral of secant squared is tangent x plus 2x squared over 2, so x squared plus 5x. Okay, now here's the deal. Plus c. However, this c is not necessarily the same as that c. So the first c could be a 3, the other one could be a -2. In order to differentiate that they're different c's, I call the first one c1 and the second one c2. Even that is not going to matter right now, okay? Because now what we're going to do is we're going to solve this for y. So y is equal to tangent x plus x squared plus 5x. And what's going to happen with the c's? I'm going to get c2 minus c1. Is that right? Well, if you have a constant minus another constant, what's the result? Yet another constant. So I call that yet another constant, and I could just call that one c now. You see that? Because it really doesn't matter how you label them. You could call it happy face if you wanted to. It really doesn't matter. It really doesn't matter because c itself can either be +1 or -2. Yep. I mean, I don't know how the AP board will look on that, but you can always try. Okay. The year when you let go, although, you know, you of all people, I doubt will be experimenting on your AP test. Okay, so here's what we have here. Okay, now, what is it that we have in this case? I have y equals this function, tangent squared plus x squared plus 5x, plus c. Why is this now not one function, but all the functions that satisfy that equation? Yeah.
Because c is a variable. I mean, no, c is a constant because the x is.
C is a constant, so remember, if I have like y equals x squared, right? And then, or if I have y equals x squared plus 2, or if I have y equals x squared minus 3, what's the difference between all those? It's the same function, except they're in different locations, right? So this too, okay, you can alternate the c's, you can change the c's, you can put in different c's, and you could potentially generate an infinite number of these graphs. They all are the same with a vertical shift, okay? So when we say here, find all functions y that satisfy this equation, what we're looking for is y equals some equation plus c. Okay? All right, question, and then we'll move on.
Why is dy? Like, why does it turn to y again?
Because the integral of dy is y. Okay? So it's the integral of 1 dy, and basically what I'm looking for there is a function for which the derivative is 1. And that function is y. Okay? Yeah. Plus c, of course. Okay, so let's do the other one. Now, in the first example, it asked for all functions y. All right? All functions y. Another word for that is the general solution. So general solution means all functions y. Okay? All right, so we're going to do the same thing. We're going to multiply dx, so I get dy is equal to secant x, tangent x, minus e to the x, dx, and I integrate. When I integrate, here I'm going to have y plus c1. And then on the right side, I'm going to have blah, blah, blah plus c2. Every single time, the c's are going to combine into one c. So I can skip the formalities, and I can just say y equals secant x minus e to the x plus c. One shot. Okay? And then, like, so as I'm solving these problems now, you know, in my mind, you know, I'm thinking about like all of the different things that this applies to, and like there is like so much that's dependent on like this, right? And okay, so we'll do a little bit, but this is like such exciting stuff we're doing right now, like such exciting stuff. Just the other day, like a student, you know, stopped me and they were like, Miss Malikian, do you know what differential equations are? And I was like, of course I know what differential equations. So I guess they heard it from another, like somebody who was like, oh, wait till you hear about differential equations. So like, this is differential equations. Okay, so notice here, for us to even be able to tackle this one, we're told x is greater than 0, right? That's going to come in handy later. Okay, so dy is going to be 1 over x minus 1 over x squared. You know what? I'm not going to write it in that form. Well, 1 over x minus x to the negative 2 dx, and then I integrate and I integrate. So here I have y equals, what's the integral of 1 over x? ln of x. However, ln of absolute value of x, right? But what is it telling us in the beginning? That x is positive, so I don't need the absolute value. I know. ln of x, okay, so minus this one, it's going to be x to the minus 1 divided by negative 1, so plus 1 over x plus c. See how we did that? So this is why, we need it to be quick and like the other stuff before. Okay, look at this one. So dy is cosine of t e to the sine of t dt. And then I integrate. And now look. Here I have y and what? It's u substitution. Here's another reason to have done 6.2 before, so we don't have to limit ourselves to just baby problems, right? So u equals sine of t, du equals cosine of t dt. This is 6.2. It's right there. So cosine of t dt is just du. And we have e to the u. So now y is e to the u plus c. Y is e to the sine of t plus c. And it turns out in math and physics, e to the sine or e to the cosine is a very, very common thing. Okay? Okay, so now we come to the more interesting parts of an initial value problem. In the initial value problem, so here, this e to the sine t plus c, this is a way that we can generate an infinite number of equations, right? But there is no way to zero in on one particular equation unless I'm given some more information, okay? So, in general, the solution to a first-order differential equation is continuous. If the general equation is continuous, right, we only need one other piece of information. All we need is a point, and that point is called the initial condition. So if you have a problem where you're given the initial condition, it's called an initial value problem, and then using that data point, you can find a single solution, which is called the particular solution to the differential equation. So the general solution, you can generate millions of them. The particular solution is one equation, y equals x squared minus 2, period. Okay? All right. So that one, you will just get y equals some function without the c. That means you have to be given information to figure out what c is. All right. So here we go. There also, the initial condition might also be called a boundary condition. Okay, so here it says find the particular solution to this equation whose graph passes through the point 1, 0. You see here we have an additional piece of information. So you start off the same exact way. dy dx is equal to e to the x minus 6x squared. So dy is e to the x minus 6x squared dx. Integrate, integrate. So I have y equal to e to the x minus 2x cubed plus c. Now I substitute my point. Here I have an x and a y. All right, in my 1, 0. So when y is 0, I have e to the 1 minus 2 times 1 cubed plus c. You see how you can solve for c now? Right? So c is equal to positive 2 minus e, which means my equation now is e to the x minus 2x cubed plus 2 minus e. Right? And there is no c in here. It's just one particular equation. There is no plus c. All right. Take a look at this one. The initial condition is given to you in different form, but it's the same exact thing. So we integrate dA. First you separate. dA is equal to 10x to the 9 plus 5x to the 4 minus 2x plus 4 dx. So integral of dA is the integral of the other one. This is a equal to x to the 10 plus x to the 5 minus x squared plus 4x plus c. Plugging in the initial condition, when x is 1, a is 6. So 6 equals 1 plus 1 minus 1 plus 4 plus c. C is 1. So a is x to the 10 plus x to the 5 minus x squared plus 4x plus 1. Okay. And so, we just have like more variation on the same thing. So here, dy dx is the secant squared equation. Separating, I get that dy is 5 secant squared x minus 3 over 2x to the 1/2 dx. Integrate. Y is 5 tangent x minus, so it's going to be x to the 3 over 2, and that'll cancel with this 3 over 2. So it's just minus x to the 3 over 2 plus c. Okay, 7 equals 5 tangent of 0 minus 0 plus c. So how much is c? 7. Oh, so I get 5 tangent x yikes, minus x to the 3 over 2 plus 7. All right, so if you look at a differential equation, right, like, did we do a very simple one yet? Well, we'll take this one, right? This is an expression for the slope of some mystery function, right? There is some mystery function. The slope of it is 5 secant squared minus 3 over 2 root x, okay? That means even if I don't know what the function is, so suppose like we take another one, right? So suppose I say dy dx is equal to 1 minus x, okay? So what does that mean? Even if I don't know what the actual function is, would I be able to find the slope when x equals 0? You just plug it in, right? Yeah, at x equals 0, dy dx is equal to 1. Would I be able to find the slope at x equals -2? Yeah. Okay, so I can potentially plug in every single value in the universe, and I could graph all of the slopes at every single point, and maybe from there, like, get an idea of how this function behaves over time, right? Something like that is called a slope field. It's literally a field of slopes. Okay? That's what it is. It's a field of slopes. So to appreciate it, okay, we'll talk about like what? So since the differential equation gives us the slope, right? What we can do, we can use the equation and we can draw a small piece of the linearization at that point. So remember how even if you have like a squared function or a cubic function, if you look at one point, it behaves like the linear tangent line. So we can draw that for each point. And eventually get a slope field. So often you will be given a problem that looks like this. I have dy dx equals x over y. And what I have to do is I have to draw the slopes at each of the points that have been identified here. Yeah. So what I do is this. So let's take this, point at the top right corner. That's the point 1, 2. Is that right? So what I do is I say, okay, dy dx evaluated at 1, 2 is x over y. So if x is 1 over y is 2, that's a half. That means here I have to draw a segment which will have a slope of 1/2. So how do you do that? So something like this has a slope of 0. Something like this has a slope of 1, right? A slope of half will look, like this. So, so that you estimate that like the horizontal is twice the vertical, So it'll look like this. Okay. You can make it that long or not that long. It's up to you. Okay, let's do another one. Dy dx at 1, 1 is 1. So it looks like that. So do you see how it looks like it has different slope? Dy dx at 1, 0 is what? 1, 0? It's undefined. Okay? So if it's undefined, we leave it blank. So if dy dx is undefined, leave blank. So now you can actually figure out a pattern. Since this is blah over y, anytime y is 0, it's going to be undefined, right? So you can just skip the entire x-axis because it's going to be undefined everywhere there. Okay? And then we get to here, 1 and -1. Well, that's a slope of -1. Okay. And then, if it's x over y, when x is 0 and y is 2, what's the slope going to be? 0. In fact, anywhere x is 0, we're going to have 0 slope for this equation. Okay, and then here at -1, 2, it's going to be -1/2. And then -1. And then here, +1. Yep.
It's like
I
you're
would hate to sit in my
dropping
room.
backwards.
It's like done is just a couple of examples, a couple of points. But when you look at slope fields in their full glory, this is what they look like. This is when it becomes more applicable to, like, real life and so on. And this is where it becomes a little bit more practical. So if you see any of these, right, like if you look back, do you see how, like, there is a trend of how something will behave, right? So if you follow like one line here, like you could see a trend in how it behaves. So this is how, even this is a small scale of how, like, slope fields are used. So we don't normally just look at 9 points. It's normally a lot larger scale, okay? A much larger scale that we look at. Okay, so let's continue and do some of the other ones. So here I have dy dx is equal to x plus y. Okay, so are there any places where you're going to have a slope which is undefined in this case? No undefined. But are there any where you're going to have zero slope? Yeah, when x and y are the same but opposite signs, right? So for example, -1 and 1, you'll have zero slope. 0 and 0, you'll have zero slope. And then 1 and -1, you'll have zero slope, right? So sometimes it's easy, to identify like that. So here you'll have at the, again, top right corner, a slope of 3. So that's kind of a rather steep line. Then you'll have a slope of 2. Then you'll have a slope of 1. So you see how, like, it will, for lack of a better term, slope down. Right. I can't. Okay. And then when x is 2, y is 0, you have a slope of 2. And then here you'll have a slope of 1. Yeah, so if you feel like it's going to be ambiguous, you can also, like, just sort of say m equals 1, m equals 2. Then you'll get the hang of it. And here it's negative. So bottom left, we're at -1 and -1. So that's -2. So this one is a little bit more, here, I'll make this a little bit more slanted. And then here, at -1, 2, you have a slope of 1. Okay.
Isn't that one 0? The -1, 1. -1, -1. Wait, no. It's not -1.
Yeah.
So what does this like show? Like, how does the function, like, what's the function that it's like any point? I just, like, I see how it's like moving in a certain
Yeah.
direction, but, like, how does that?
We'll talk more about this one. So let me,
Just like a visual representation of what the slope looks like.
Yeah.
So you kind of like go backwards, I would guess, so you can see where there's a specific point where they did it.
yeah.
Mm.
Okay, so here it's -1 over y. So we're just going to look at the y values. That means if it's -1 over y and it doesn't depend on the x's, that means on a given, like, vertical level,
Anything
they're all going to have the same slope, right? So if you're at y equals 0, it all has the same slope. Y equals 1, same slope. Y equals 2, same slope. So if you're at y equals -1, it has +1 slope. Y equals 0, you have undefined. Y equals 1, you have -1. And then y equals 2, you have -2. Okay? And that is section 1. So now, so take a look at this problem, number 64. It says, which of the following differential equations would produce a slope field shown below? So you would have to, match this to this, right? And you have to look at trends. the best thing to do here is to eliminate things that you know are not going to work. So for example, if you look here, right, some slopes are negative and some slopes are positive. Is that right? So right off the bat, C and D would be eliminated because by taking absolute values, you're just making all the slopes positive, right? So you eliminate that one. And then some things we would look at is, okay, is there, like for example, if it was like 1 over y, right? Something like that. You know, you would have to say, okay, is there like one line, either horizontal or vertical, where all the slopes are 0 or all the slopes are what do you call it, undefined, and so on. And so now what we are left with is A, B, and E. And so what you can do is, you know, try a couple of points and see, you know, which ones, when you put them into these equations, will work. So for example, the point here where it looks like it's at x equals 0, y equals 1, right? That has positive slope, right? So x equals 0, y equals 1, and then like you would try to see and eliminate, you know, which ones will work and which ones will not work. Okay? So that's how we do those. Okay.